some of modern physics, looking into quantum mechanics and some nuclear physics. One of the issues that led into the new physics was the issue of blackbody radiation. So according to classical physics, which includes Newton's laws and things of that nature, but according to classical physics, the energy emitted by a black body, remember a black body is a perfect absorber and emitter, and we talked about those a while back in our thermodynamics chapter, but a problem with classical physics was that it predicted that for a given temperature there would be an infinite amount of ultraviolet energy being radiated, which obviously doesn't make much sense, and that was referred to as the ultraviolet catastrophe. And it was a major problem because blackbody radiation is something that it doesn't depend on the material. And the reason that's significant is because if something doesn't depend on the material in question, it only depends on the temperature, in the case of blackbody radiation. But if it doesn't depend on the material in question, that probably means it's related to some fundamental things about the way the universe operates. And if you can't explain something like that, then that's a serious problem for your theory. So there's this serious problem with classical mechanics, which had been very successful for, like 300 years prior to this time. This is in the late 19th century, getting on toward the early 1900s. And the guy there was a guy who was doing stuff related to blackbody radiation called Max Planck. And he's the one that ultimately, he figured out how to quantize blackbody radiation. Then Einstein took it further and started something of a revolution in physics. But I'm getting ahead of myself here. All right. So the experiments show that for a given temperature, there's a curve that looks something like this, where the intensity, there's a relationship between the intensity and the frequency of light. So for a given frequency, if the frequency is 0, intensity is 0, okay, that doesn't, whatever. But there are curves that look something like this, where there is some frequency of light that is there's a high intensity of that light being emitted, and then lower intensities on either side of it, and the curves go off to, as the frequency gets higher and higher, there is ultimately 0 intensity of the highest frequencies being emitted. So they have this same general shape. And if this is for some temperature, say T1, if we have a second temperature, for temperature T2, the curve is kind of bigger like this, and this peak shifts over. I didn't draw that very well. But if for a given temperature, this peak frequency is proportional to that temperature. Okay, and that's quantified. The frequency of that peak is at 5.88 times 10 to the 10th times the temperature. So there's this linear relationship between this peak frequency and the temperature. Right? And as temperature increases, the area under this curve increases, which means that higher frequency implies higher energy. Okay, and that's all very reasonable, but the prediction from classical physics was a curve that looked something like this, that just went up to infinity, and that didn't make a lot of sense. And it went up to infinity in the ultraviolet range, which is why it's called the ultraviolet catastrophe. So Max Planck was finally able to resolve this by coming to what was really a revolutionary conclusion. Planck said that energy is quantized, meaning that it comes in discrete packets. So there are certain energies that you just can't have because they're not multiples of this fundamental quantum of energy. So just like charge, we talked about, charge is quantized. You can only get multiples of the electron charge. Planck said that energy is also quantized. Now, going back a ways, when we talked about gravitational potential energy, we said that was minus g m1 m2 over r, or near the Earth, that was about mgh. And then there was spring potential energy, which was a half kx squared. And for these, this x or this height or this radius could all be any value. Well, and Planck's coming along and saying that energy, they in fact can't be any value, and that they can only jump in discrete amounts, which is really sort of a bizarre kind of result. So let's take a look at what he said. So he said that the energy radiated by a black body was equal to n, which was just n is 0, 1, 2, 3, 4, whatever, it's just counting numbers. So the energy has to come in multiples of h, which was a constant, times the frequency. And this h is Planck's constant. He discovered it, so he got to name it after himself, I guess, or maybe they named it after him later on. And that h is equal to 6.63 times 10 to the minus 34th joule seconds. Okay, so Planck was saying that the energy radiated by a black body, well, he just said, I shouldn't say it, he said energy is quantized. He said energy radiated by a black body is quantized. Okay, and that's kind of a crazy sort of thing. Let's consider for a second, just to show you what this means, a system that we've already discussed. Let's say we've got a mass on a spring. That's a situation we discussed back in the early beginning of the second quarter, I believe. And we know for a mass on a spring, the angular frequency of its oscillation is square root of k over m. Okay, so, given fairly reasonable values, say we've got a k of 15, spring constant of 15 newtons per meter, we've got a mass of 0.65 kilos, then let's see what this indicates. Well, then we've got an omega of square root 15 over 0.65, which means that we have a frequency, and frequency is omega over 2 pi, a frequency of square root 15 over 0.65 over 2 pi, which means that the allowed energy states are equal to h 6.63 times 10 to the minus 34th, times f square root 15 over 0.65 over 2 pi times n, which, if you multiply it out, comes out to 5.07 times 10 to the minus 34th times n. So these are the possible energies of this mass on a spring, right? And that energy is determined by the initial velocity it's given or how far it's stretched or whatever. But this is saying that the spring can only be stretched to give it energy that's multiples of this. Now this shows us two things, both of which are kind of revolutionary. So even the energy of this spring changes in steps. Even though classically this spring could be stretched to any distance you want, quantum mechanically that's not allowed. And the other thing, this also shows us why they didn't notice that energy was quantized for hundreds of years, because this is something on the order of 10 to the minus 34th, which is really, really, really tiny. A difference of 10 to the minus 34th in the energy is a difference of something on the order of 10 to the minus 17th in to even get an energy that small, you have to be at 10 to the minus 17th for your value of the distance. So, that explains why it took them so long to figure out that energy was quantized. Now, this result, this black equation for energy of blackbody radiation, it worked. People didn't really like it because they had this whole system of classical physics that worked really well for most things. And there's just kind of this equation floating out here that seemed like it was just sort of a mathematical trick that made blackbody radiation work, but it didn't really fit in with everything else. And that didn't sit well with a lot of people. And that brings us to perhaps the most famous physicist there is, along with Newton anyway. Einstein enters the scene, and he takes care of this problem, as it were.